Swayam Prabha. Digital India. Educated India.
Hi, and welcome back to this lecture series on Foundations of Cyber Physical Systems. So, I believe in the last lecture we have been talking about this CAN-bus worst case response time analysis, and in the process we were introducing this idea of busy period and how the busy period can be computed. And we then said that, well, for finding out a response time for a specific message, what you need to do is, inside the busy period you have to figure out how many instances of this message has really been transmitted. So, let us say the busy period is TMI okay, for this message. That means it has been blocked initially, and then there has been multiple transmissions by other higher priority messages, and eventually all the release instances of the message of this particular message got transmitted, right. So, that has been our definition of the busy period. Now, so if this is this length is greater than the period of the message, then I would be having multiple instances of the message, and I would have to then figure out, well, if there are q instances, let us say from 0 to qmi minus 1, qmi is computed like this. Then for all these q instances, 0 to qmi minus 1 number of instances, I will have to figure out what is the worst case response time and what is the response time, and eventually the worst case would be the max among these. So, that is how we go forward and do this. So, for our example here, if you recall our example, so we figured out this is the length of my busy period, right, for this particular message, and inside this busy period, M1 has got two release instances, one being here and the other being here, right. So this was M1's first instance and this was M1's second instance here, right. And so inside this overall busy period of 38 milliseconds that we calculated, for the first instance, as you can see, I mean the first instance has the release here and the transmission ends here, right. So the busy period is given by this value, which is like if you can see, it should be 12, 8, 8, so that's 28, and 5 is the execution time of M1, the transmission time of M1, so that's 33, right. And for the second message's response time, again inside the busy period we have to see when it arrives here, right, and it has a period I believe of 30, right, and it has to wait for some time, I mean this 3 milliseconds, and then it will be executing for 5 milliseconds, right. So that would have a response time of 8, right. So if we want to check, let us just go back and see the task setting here. Yes, so M1 has the periodicity 30 itself, so as we can, and M1 has a transmission time of 5, so that means this indeed comes at 30 and the busy period length is 38. So definitely the transmission time is 8 milliseconds here. Okay, now definitely the max would be 33, so that's the worst case response time. Now the question is, well, how do I compute this response time for each of these messages? Because here we are doing it just by looking at the picture, the schedule on the busy period, but how do I do it computationally? Well, we will have a similar kind of recurrence equation for that. So what we will do is, we will figure out the longest time from the start of busy period to the instance q. So let us say we are looking for some qth instance of message mi, and we are trying to figure out its response time. So the first thing I will check out is what is the time starting from the initial I mean from the start of the busy period up to the situation when this qth instance of mi has started transmission. So let's call these things. So this is for qth instance, right, 0, 1, 2 up to q, right. So for this many for this to start, what is the duration? So let's denote it by w mi q, qth instance of message mi start of successful transmission. Okay, Now how can I figure it out? Well, it would be blocked initially by the blocking time for this particular message mi, and then we would have this, if you see, this is the qth instance, and the indexing in this notation here is starting from 0 up to q minus 0 up to q. So before qth instance we already have q number of messages with index 0 to q minus 1, right? So for this q minus 1 messages you have this much of transmission time taken up, right? So you have an initial blocking time at the time when this was getting blocked by lower priority messages. You have inside this space, what are the things we are having? We are having the blocking time, and we are having the time when the previous instances of this message themselves got transmitted. There are q such instances, 0 up to q minus 1, and then you have the interference time. So the way I will calculate the interference time is, I will see what are the higher priority messages, and I have a previous estimate of this quantity, add with it tau bit, which is the transmission time of 1 bit, assuming this is where the first bit of this particular message starts transmission, and you are dividing this by, this message's periodicity. So for whichever message has got the higher priority, so let's say you have multiple messages who have got higher priority than mi, right? So let's pick one of them m. So you divide this previous estimate plus tau bit, this small delay, divided by the period of this message. So that would give you how many instances of this higher priority message is kind of interfering with this, and those instances definitely will be transmitted earlier. So you have to multiply this with the transmission time of each of those messages, transmission time of those message instances, and then you have to similarly sum it up for all such other high priority messages. So that's how you do it, and this gives you the time starting from the from the start of the busy period up to this time when this particular message, this qth instance of mi, starts its transmission. So you can compute it like this. Now this is not really what we are looking for, right? We are looking for the response time. That means if I go by response time definition, it is the time. So this is basically this current estimate is giving me when this message actually starts the transmission, right? So this message will start the transmission here, and if you add the transmission time, right? So if you add this quantity with the transmission time, then you get the time value when this message transmission is successfully finished, right? But we want to subtract from it the time when this message actually arrived into the system, right? Because we are calculating response time. So the time when the message actually arrived in the system, the qth instance, is basically given by the period of mi multiplied by q, right? So you just subtract this q times the period of mi, right? And that would give you, so this is finally going to give you this response time of q. So now you can, just like our previous computations, you can keep on solving this recurrence multiple times until it stabilizes, and you get the overall waiting time, right? And then you use this waiting time in this equation to get the response time. So that's how you can simply do it. So you can start your initial iteration with this being 0, and you are having this b, the blocking time, plus qcmi, and then eventually you will stop when under 2 successive iterations these values are same. Okay. So if you can see this example, let's say we are talking about message 0, right? Message 0 has a blocking time 0, and so you have this as 12, and then so you are looking really for the 0th instance of message 1, right? Sorry, not message 0, this is message 1's 0th instance. So that is 0 multiplied by 5. Then basically it's just the initial blocking due to the other lowest priority message, right? And then you can compute W1, so that's 12, and then you can compute in the next iteration. You can use this here, right? So this is the busy period's current estimate. This is W's current estimate. Tau bit, we are always neglecting tau bit here. For all practical purposes we will just neglect it unless it has a bigger value. Okay, So we will just neglect it, and we will have this and this messages transmission time is 8, right? So and the periodicity is 20. So this is about the message which has the higher priority with respect to M1. So that is M2, right? So you are giving the interference due to M2, and you have the wait time estimate to be refined to 20, and then it gets further refined to 28, and it stabilizes at 28. So this waiting time is 28 here. So then you can use 28 for the 0th instance of M1. So basically this message, right? And as you can see, for this you can calculate the response time like this 28 plus 5, which is the actual transmission time. So that would give you 33. And if you check, this checks out, right? Because the arrival is right at 0, so nothing really to subtract. So and this interval is really 28 plus 5. So and this is the wait time, right? Up to the time when this really starts this transmission, and before that actually you see you had 2 iterations of this equation, right? I mean that's really happening because there are twice you have to factor in the interference due to this message instance of M2. You have this message instance of M2 coming right here, 1. So you have this interference, another is coming here, so you have this interference, and that's kind of getting added up through these 2 iterations of these equations, and then it stabilizes. So now similarly, if we are trying to do it for the next iteration, so let's if you see here we talked about 2 different instances of M1, right? So we computed here for the 0th instance, but you also have the first instance here, right? So if I try to compute this wait time for the first instance, so this is the first instance. So the usual blocking time plus now you have 1 instance earlier, so you will multiply its execution time here. So the transmission time for this message is 5, and for M2 that is 8, right? Now if I just try to refine it further, so you will have another 5 here, and another 8 here, so that is 33. And if you try to refine it further, so if you just check this out, so you see that now this has stabilized, right? And this is kind of the final answer here, because eventually it's now always coming to be the same expression. So we can just stop here and now you have got one idea, like well, from my previous calculation for the 0th instance of the message F1, we computed, just recapping here, that this waiting time was 28, and you use the response time equation for this 0th message instance, and you got the entire response time as 33 here, right? And we are now trying to calculate for the first instance, and what we saw is that for the first instance the wait time was 33, and then you apply the response time equation for the first instance. So 33 minus the arrival time when it came, that is 30 plus 5, that's 8, right? So if you see this equational method that we discussed, that is kind of agreeing with how we analyze the busy period and response time from the figure. And now you can just apply our previous definition of worst case response time and calculate and infer that the worst case response time would be 33 here. So that's how we calculate worst case response time of messages in the bus in case of any fixed priority non-preemptive scheduling algorithm, which we took as an example as CAN, but it should hold in general, as you can understand. So if I just quickly summarize what had been this response time analysis method, what we started with was blocking time computation, and for some message mi, it gave me this PMI, right? And then using that we computed busy period, and then using busy period we computed number of instances of mi inside this busy period, and then what we did is we calculated the response time of each instance, and then we took the max of the previous calculation, right? So from BMI we calculated the busy period using that recurrence equation, right? And we got this time for the busy period, and then we computed the Q number of instances, right? And that was containing this 0 to up to some Q elements, whatever. And for each of these elements here, we computed the response times, right? And then you applied the max over them, and that kind of gave you the worst case response time here, right? So this is how overall you are given, if you are given a CAN or some other bus-based system, maybe a TDMA or this kind of a fixed priority non-preemptive bus scheduling protocol, and they are connected with multiple compute units where these individual computer control units, whatever you call them, they are containing tasks which have precedences, and they are scheduled with respect to some scheduling algorithm. How you schedule the tasks in the processors and how you schedule the tasks in the bus. So that's overall our coverage of how real-time scheduling works in general, and in our later lectures we will see that how this affects cyber physical system design. For any kind of such design, timing analysis, as you can understand, would have been a very important criteria, and these are some of the basic techniques of timing analysis which are applied in the industry and will if you are trying to do research in this area in both places. So with this we will end this lecture. Thanks for your attention.